zoomed it back out. For the,
I'm not sure if I'm afraid.
The notes is over there, sir.
well, that should be okay for you.
Yeah, you're good there.
Yep. There you go.
Is that okay?
Yeah.
Okay, thank you. This one is not right.
This one is
Okay,
that one.
okay.
Amplification.
Okay, thank you.
Do you, when you finish it?
5 o'clock. Yeah, all right, see you.
I think that's mine. Have you put one of those in there?
Sorry?
Is this yours? I just gave a lecture in here.
Okay.
And I think I left that. That's not yours, is it?
No.
No. Thank you.
Hello. Good afternoon. Has all of you got the handouts? There should be 3 sets of handouts that you should have got by now. If you haven't got it, can you shout? Can you just shout at one of those people who's standing up? They will come and give it to you. If you haven't got any of the handouts, there are 3 handouts you should have got. One of them looks like this. This is the course outline. Yeah, this is the first handout. The first handout you should have got. The second handout should be looking something like this, examples. And the third handout is this one, which contains the lecture notes. Right? So if you haven't got any of these 3 handouts, could you please raise your hands so that one of them can give it to you, please. Anyway, first of all, welcome to Statistical Methods, Math 20802. My name is Saralis. I'm the guy who has been sending you dozens of emails, bothering you. I've been teaching this course for the past 9 years, and this is the 10th. This is the year 10, the 10th year I'm teaching this course. It's kind of special for me. So it's gone, the course has gone well over the past few years. And I hope you guys behave, because I would like this special year to go very well, if possible. All right, let me just briefly talk about the course, right? This is the syllabus for this course. As you can see, there are 2 lectures per week. One today and one tomorrow. And there are four example classes. You need to attend only one of them, right? You need to attend only one of the 4 example classes. And if you look at your timetable or My Manchester, it will tell you which of the 4 classes you need to attend. But if it happens that the class that you are allocated to is not convenient to you, I mean, it may be that you may have a clash with some other class, or it may be that you have some personal reasons not to attend the specific class. In that case, you're most welcome to attend any of the four example classes. You don't need to stick to the one that is in the system. That's what I'm saying. You know what I'm saying? Yeah. So you don't need to stick to the example class that you are allocated to, right? Just feel free to attend any one of the four example classes. And these are the times and the places. All of them are in Alan Turing Building, and Tuesdays 2 times, Thursdays 2 times. This is my office, my phone number, my office hours, the course this is the course website, right? Now, I'm usually in my office Tuesdays to Thursdays. Sorry, Tuesdays to Fridays, I meant. 11 to 4 p.m. or 11 to 5 p.m. So, although I have office hours from 1 to 2 on Tuesdays and Thursdays, you are most welcome to see me anytime during or outside the office hours, right? I'm most happy to talk to you, go through any problems that you have, all right? During any time I am in my office. You can come and see me without making an appointment, right? I'm happy to talk to you and help you in any way I can, right? This is the course website. I'm sure I sent this this website here, right? It gives you everything that you need to know about this course, right? It contains the lecture notes, it contains the syllabus, the problem sheets, solutions, exam papers, past exam papers for the last 9 years, and the solutions for the past 9 years, the past in-class tests and the solutions, and so on. And it also includes the student feedback for the last 2 or 3 years, right? So you can see how this course has gone in the past years, right? Right, now, the course website also includes the podcast. I think I mentioned in my email to you guys that every lecture, every tutorial will be podcasted, right? And immediately after the lectures and tutorials, the links for the videos will appear on this website, right? So as soon as I go back to my office, I will try to put the link for the videos, the podcasted videos, in this website, right? One thing I like to mention is that there are some lecturers at this university, they use something called Blackboard. I'm sure you heard of that term. But personally, I do not like to use Blackboard for various reasons. I think it is much better, right, if I put everything online, right, open access, so that you can access it from anywhere, anytime, right? So everything you need to know about this course is under this website, right? Whereas in Blackboard, sometimes it's offline, sometimes it's down. Like my Manchester is also sometimes down. Sometimes it's down for the whole days. Sometimes several days it's down. So it's really a pain in the neck, and when such a thing happens. So for that reason, I prefer not to use Blackboard. So please don't complain, or don't send me emails saying where my stuff is in Blackboard, because I don't use Blackboard. Okay, I think it's only for your interest. I mean, yeah, I think it helps you a lot not to use Blackboard, right? Because by putting everything in this website, you can see it anytime, anywhere you are, right? You can download the podcast, the handwritten notes, and everything. All right. these are two prerequisites for this course. I know most of you have done these courses. If any of you hasn't done this course, please see me after the lecture, right? I know in semester 1 you took one of these courses, it's the probability 2. I hope it went, it go okay, guys? Yeah? No. Well, why you don't talk to me, guys, please? I hope it went okay. And this is a brief content of the syllabus. And there's no need for textbooks unless you really want to buy something, it's okay. There is an assessment. All right, this is where I need to be clearer. There's an assessment on the 26th of April, which is a Wednesday, the first Wednesday after the Easter break. I know this is kind of late in the semester because I think this is week 10 or something, if I remember correctly. But the reason I have put this, because I mean, over the years I've taught this course, the in-class test has always been after the Easter break, right? So that's why this year the in-class test is going to be on week 10, because Easter comes late this year, okay? And this in-class test will account for 20% of your final mark, and the exam in May or June of this year will account for 80% of your mark. And I also plan to, I mean, it's not official yet. I also plan to give a bonus question, right? That will account for 2% of your final mark, right? So the total will be over 100. You should get all of them correct. Yeah. Okay, that's something. I mean, it's not something I have finalized yet, but I will let you know later, right? Whether I will give. In all probability, there will be a bonus question, right? But in any case, I will let you know later, guys. Okay? All right. Now, so any questions so far? All right. So that's the syllabus, right? Course outline. This is the second handout I gave you. It gives you a list of examples. If you look through this, there are close to 90 examples. Okay. I will, by the end of this course, I would have gone through most of these examples, right? All right, and the solutions to many of these examples can be found on my website. So once again, if you go to this website, you will see the solutions to most of these examples, right? Not all of them, but most of them. The solutions to most of these examples can be found here, okay? And this is the lecture notes, right? This is the lecture notes for this course, right? All right. Now, let's begin. first thing I want to talk about the first thing I want to talk about is the moment generating function. I know many of you, or perhaps all of you, have done this in the past, right? The MGF, right? All right, for a random variable x, the MGF of x is defined as the expected value of E of t times x, okay? Where t is a fixed number, t is a fixed t is a fixed real number, right? Okay. If x is a continuous random variable, yeah, then yes, yeah. If x is a continuous variable, then the moment generating function is given by this, where this is the PDF of x, right? PDF stands for probability density function. Okay. Now, if x is a discrete random variable, right, then the MGF can be defined by this, right, where this guy here is the PMF of x. PMF stands for the probability mass function, right? All right, so this is the definition in the continuous case, that is, if a random variable is continuous, and this is the definition if a random variable is discrete. But there are also cases where, there are also random variables that are neither continuous nor discrete. But I shall not talk about them in this course, right? Just for reasons of simplicity, we will just limit to these two cases, continuous or discrete. Okay? Okay. All right, guys. So put this here. Oh. Okay. Properties of MGF, right? One, right? The first property says that the kth moment, I mean this, we refer to this as the kth moment. The kth moment of a random variable is the kth derivative of the MGF at t equal to 0. All right, so this is what it means. The kth derivative of the MGF at t equal to 0. Right? All right, this is the second property, which says that the expectation of x is simply the first derivative at t equal to 0. The variance of x is given by this. Right? The third property says the following. It says that MGF of AX plus B is equal to this, right? Property 4 says right? It says that if you have two variables x and y, and their MGFs are equal, then that must imply that x and y have the same distribution, right? Okay. But this property, one thing I must say about this property is that this strictly speaking, this property does not always hold, right? In other words, there you can have there are examples. I will not go into those examples in this course, but there are examples where two variables x and y have the same MGF, but x and y right? X and y do not have the same distribution. But these are kind of isolated examples, if you know what I'm saying. I mean, for the purpose of this course, I will assume that property 4 always holds, right? But as I said, there are examples where it does not hold, right? Okay? But at least for this course, we will assume that this property is true, okay? Okay? Now, property 5 if you have random variables xi, I from 1 to n, independent random variables, and if they have MGF denoted by this, right, then the MGF of the sum, that is x1 plus x2 up to xn, is given by this, right? This is a really important property. We will use that in the example class later on today, and we use this in the example class from 3 to 4 this afternoon, right? Okay, and so these are the five. There are many other properties of MGFs I can give you, but these are the 5 main properties of moment generating function, right? So let me show you how to prove some of this. proof of property 1. This is property 1. Okay. To prove this, you can prove this in several different ways. We know that M we know that the definition the definition of an MGF is this, right? Okay, guys, so take the derivative. All right, which is okay. All right. So the derivative, taking the derivative on both sides, left and right, this is what you get, right? Now if you set t equal to 0 on the left and the right, you will get this, right? The right-hand side becomes the expected value of x times e of power 0, which is 1. So this is proved. Okay. Now take the derivative of this one more time. So from this, you should differentiate that with respect to t one more time. You get right, which is okay. Now setting t equal to 0 one more time, you get this. Okay. You guys okay? Right. Next, you repeat this process over and over again. So if you differentiate this one more time, you get the third derivative. Okay. Now set t equal to 0. Set t equal to 0, you get equal to expected value of x cubed times e of 0, which is x cubed. So if you repeat this process a sufficient number of times, right? The result that you will get is that the kth derivative at t equal to 0 is equal to the expected value of x power k. So that proves the first property number 1. Okay. Now this is not an elegant proof, but I know most of you guys are mathematicians. You probably know more than me about mathematics. I would like you to prove this as a homework. Prove when you have time, right? When you have time, please could you prove this property here by mathematical induction. I'm sure you know what mathematical induction is. You guys know? Yes? Yes. So try and see. I'm sure it's not difficult, but try and see if you can prove it by mathematical induction. Okay? All right. So that's all right. That's proof of one. Proof property two. Sorry, property two is trivial. Property three. So let me show you how to prove. Let me show you how to prove property 3, okay? So you start with the MGF of AX plus B at T, which by definition is equal to this, yeah? Yes. Now, this you can write as this guy is a constant, so you can pull it outside the expectation sign. So this becomes E of TB okay. And finally, this is E of TB, and this guy here, by definition of expectation, sorry, by definition of MGF, this is the MGF of X at TA, and therefore we have proved property 3. Okay. Property 4. As I said, this property is strictly not true, so I mean, I'm taking this property to be true, nevertheless, for the purpose of this course, okay? All right? And property 5, is this property here. So let me show you how to prove it. Okay, proof of this property. So you start with the left-hand side, which is the MGF of T, right? Okay. Yes, and this is equal to this, right? Okay. Now, we are told that xi's are independent random variables, right? So using independence, remember, a property of independence is that if two variables are independent, then the product of their the expectation of their product is the same as the product of the expectations, right? So I'm going to use that property here and write this okay. Yes. Now this, by definition, this is the MGF of x1 at t. and this is the MGF of xn at t, right? So we have proved that the left hand side is equal to the right hand side, right? Okay, guys, so that proves property 5. Any questions so far, guys? Just a reminder, if you want to copy that, if you want to copy down what I write here, that you are most welcome. But as I said a few minutes ago, everything I write, everything I say here will be recorded, and they will be put online in the course website, right, soon after the lecture, right? Okay. So unless you really want to, there's no need for you to write it down. Okay. Okay. All right, guys. So that's all on MGFs. Now, you should turn to the next page of the lecture notes. That is page 2. This is page 2 of page 2 of the lecture notes. It's a kind of a summary. I'm sure you've seen these distributions before in probability 1 or probability 2, the courses that you have taken before. But I will briefly run through them, right? I will just run through them very briefly. Okay, so all right, starting with the first one. For a Bernoulli variable is defined as a variable x that takes two possible values, either 1 or 0, 1 with probability p, 0 with probability 1 minus p. The expectation of a Bernoulli variable is p. The variance of a Bernoulli variable is p times 1 minus p. And the MGF of a Bernoulli variable is 1 minus p okay, and the notation I shall use this is the notation I shall use to denote a Bernoulli variable, a random variable, right? So these are some basic properties of a Bernoulli distribution, and you should be able to derive this by yourself. I mean, okay. If you have problems with deriving this, please send me an email or come and see me. Okay. So that's number one. Number two. number 2 is discrete uniform. There are two kinds of uniform distribution. One is called discrete uniform distribution. The other one, which we'll talk about later, is the continuous uniform distribution, which is different from the discrete version. Okay, the discrete distribution is defined. It takes the values is defined by this. It's a variable, it's a random variable x that takes the values x1, x2 to xn, each with probability 1 divided by n, and others with probability 0, right? The expected value of x, once again, I mean, every time I write down something, an expression, but do not show the derivation, please try to derive by yourself, because I don't have the time to derive every single equation in this course, because I meet you guys only 2 hours a week plus the example classes, right? So I would like you to try to derive everything I write down by yourself, right? And see, if you can't do it, please see me in person or send me an email, okay? All right, the expected value of a discrete variable is this, right? The variance is this. The MGF of a discrete uniform variable is this. Okay. All right. Okay, guys. Just one more. The next one, number 3, is the binomial, right? The binomial is defined, the variable x is the, is the number of, I'm sure you've done binomial before, right? Sorry. Is defined as the number of successes. A success it corresponds to this one here, right? Success is represented by 1, failure is represented by 0, right? So it's the number of successes in a sequence of n Bernoulli P trials, right? And in this case, the probability mass function, let me change this to m, right? The probability mass function is m choose x px, all right? And x takes the values x takes the values from 0 to m. The expected value of x is equal to m times p. The variance of x, m times p times 1 minus p. The mg of x, just work it out, okay? Work it out by yourself. This homework for you guys. Okay? Try and see if you can do and find the MGF of a binomial random variable. All right, guys. So I'll see you guys tomorrow or later today, because we've got example class now from 5 to 6 in one of the rooms in Alan Turing. Okay? Just a minute, man. There must be. Don't you have? Can you come to my office now? Can you come to my office? Yeah. Okay. Come to my office. I will give you one. Do this one. Are you in the example class today? Yeah, you should do this one. Yeah, this one is the same. It has the same examples. Yeah. Yeah. I think that's the correct answer.
Okay.
I don't.
Beats.
I think there's a mistake here. Yeah.
Okay, thank you very much.
Well, see you, man. See you. Yeah.